No branch of science can claim to have a bigger area of interest than cosmology. For cosmology is the study of universe, and the universe by definition contains everything. Although because of its profound implications, cosmology has traditionally its philosophers and religious thinkers. Our approach to the subject will be through the science of astronomy. Astronomy is taught as a study of the properties of planets and stars and gradually restored to include the limits of the Milky Way system, which is our galaxy. Modern astronomical techniques have taken the subject beyond the galaxy to distant objects from which light may take billions of years to reach us. Cosmology is concerned mainly with this extragalactic world. It is a study of large-scale structure of the universe extending to the distance of billions of light years, a study of the overall dynamical and physical behavior of billions of galaxies spread across vast distances and of the evolutions of this enormous system over several billion years. At first, such a study may appear an ambitious task. Are our tools of observations good enough to provide sufficient information about the large-scale structure of the universe? Is our knowledge of the laws of nature sufficiently advanced and mature to interpret this information? By the way, of an answer to these questions, we quote a remark of Albert Einstein. He said that the most incomprehensible thing about the universe is that it is comprehensible. Although our observation techniques are far from perfect and our knowledge of physical laws leaves considerable room for improvement, we are still in a position to make some sense out of what we observe, which is why we can begin to study cosmology as a branch of science. That is, we will take the large-scale structure of the universe as a physical system subject to the known laws of physics and follow the usual procedure of science, that of observing features of relevance to this study and then trying to interpret them and making predictions that can be tested by future observation. Nevertheless, our success in interpreting the universe through physical models should not blind us to the enormity and depth of the basic questions that emerge. The model may, at best, represent a first approximation to reality, which could still be elusive. We will begin with a brief survey of some of the features of the universe that are pertinent to the subject of cosmology. Before coming to the present understanding, however, it is instructive to present a brief historical review of how this understanding was arrived at. Length. The physicists use meter for SI units or centimeters for the CGS units. While we shall use the latter in deriving quantitative expressions from physical formula, they are too short for cosmic distances. The physicists would have preferred the light year, that is the distance traveled by the light in 1 year, while the astronomer prefer to the parsec, a unit that naturally arises when one is determining stellar distance by using the method of parallax. 1 parsec is defined as the distance at which half the diameter of the Earth orbit subtend an angle of 1 arc second when it is looked at symmetrically from the normal direction. Large units constructed from the parsec, PC, or kilometer. Time. The basic unit of time is of course the second, but on occasions cosmology demands much longer time scales. The typical unit is the giga-year, and 1 giga-year is equal to 10 raised to the power 9 years. Mass. The physicists may use the kilogram SI units or gram CGS units, but masses of astronomical objects are best expressed in the mass unit of the sun mass, which is 2 multiply 10 raised to the power 33 g. From Herschel to Hubble, In the history of astronomy, the era of William Herschel stands out as one when astronomy expanded its frontiers beyond the solar system to look at stars in the Milky Way. Although Herschel shot into fame largely throughout his discovery of the planet Uranus, the first ever new planet to be discovered in recorded history. It was his study of stars that gave a first understanding of what the Milky Way is, namely that it is a distribution of stars in a disk spread all around the sun, such as distribution of stars on a large scale is now known as galaxy, with the Milky Way being called the galaxy. The picture with the sun at the center of the galaxy remained the accepted picture until the beginning of the 19th century. The distance to stars in the galaxy was determined in the early days by the trigonometric method. Unfortunately, this method loses accuracy beyond 50 to 100 BC. Furthermore, the dark patches in the Milky Way are not due to the absence of stars. Interstellar dust may exist in several forms such as graphites, silicates, and solid hydrogen. The effect of dust is to reduce the intensity of light from distant stars in the galaxy through absorption and scattering. In the early days, astronomers overestimated stellar distance in the galaxy because they failed to correct for interstellar extinctions. The earlier astronomers also mistook dark regions for holes or empty regions in the galaxy. A more reliable method that made use of the variable stars called Cepheids became available in 1912. Harlow safely used this method to measure the distance of remote stars in our galaxy and show that our galaxy was much larger than it had previously been thought to be. The revised picture of the overall size of the galaxy also meant a change in the perceived locations of the sun and its planets. But not before several debates between those such who believed that the sun was more or less at the galactic center, and a small minority represented by Shapley who placed it considerable far from GC. We have to follow for the fact that unlike other galaxies which we can look at from outside, the shape and size of Milky Way galaxies have to be determined by the observations. The picture of spiral structure of the galaxies, whereas the edge on the picture demonstration that it is a disk with a central bulb. The disk is also referred as the galactic plane. The diameter of the disk is estimated to be 30 kpc and its thickness is 1 kpc. The sun together with all its planets is located at 10 kpc from the center. The galaxy rotates about its polar axis, although not as a rigid body. How the circular orbital velocity varies at different distance from the GC. The sun, for example, takes 200 million years to make one complete orbit. Like the sun, many other stars also go around the galactic center, whereas some stars have highly eccentric orbits that take them out of the galactic plane and also very close to the GC. Absorption lines in the spectra of galactic stars show that absorbing gases are present in the interstellar medium. Gas appears in various forms: atomic and molecular, hot and cold. Emission nebula around stars are made of gas that absorbs the ultraviolet radiations from stars and radiate its visible light in spectral colors. The so-called hydrogen regions are hot regions near stars and contain hydrogen gas that has been ionized by the ultraviolet light of the stars. In contrast, the hydrogen regions are cool regions of atomic hydrogen. It took a few years longer for astronomers to appreciate the extragalactic nature of the universe. The general belief at the turn of the 20th century was that all the hazy nebula were located within the Milky Way. The idea proposed by a few astronomers that the nebula were galaxies of stars similar to the Milky Way. The 1920 Hubble discovered that certain bright nebulae previously considered part of the galaxy were actually remote objects lying well beyond it. Hubble discovery finally laid to rest the belief that the whole of the observable universe was contained in our Milky Way, an island floating in infinite space. The nebula that Hubble had proved to be extragalactic turned out to be galaxies in their own right. The idea that our galaxy may be one amongst many populating the universe, and that all such galaxies are like islands in vast space, had in fact been proposed by Kant in the 18th century and had been known as island universe hypothesis. It receives confirmations through such observations. Today the astronomer has a much better perspective on the vastness of the extragalactic world. The following section describes broad features of various types of galaxies known today. There we shall also see that the galaxy appear to contain dark matter that extend substantially beyond their visible boundaries. Types of galaxies. The spiral structure of our galaxy was difficult to establish observationally since we view it from within. It is easier to see this structure in other galaxies unless we are viewing them edge on. Our nearest large galaxy is Andromeda Galaxy, has a similar spiral structure. Spiral galaxies, as such as galaxies are called, are probably the most numerous amongst the various types of bright galaxies. Like our galaxies, they exhibit rotations, flattering with a central bulk and dark lens of observing matter. In 1926, Hubble classified the various types of galaxy in the following way. The various classes of spiral galaxies are called SA, SB, SC, and so on. The sequence in decreasing order of importance of the central nucleus or bulk in relation to the surrounding. Along the sequence, the central spheroid has decreasing luminosity, and the spiral arms become more loosely wound. Our galaxy and M31 are of type SB. Some spirals have bars in the central region. These are called barred spirals and are categorized as SBA, SBB, and so on. While spirals are the most numerous amongst bright galaxies, the most numerous amongst all galaxies are those classified as ellipticals. These are ellipsoidal in space, exhibit very little rotation, and have very little gas and dust. The various types of ellipticals are placed in the sequence E0, E1 up to zone E7. This sequence describes progressively flattened profiles of galaxies, E0 being nearly spherical and E7 of markedly flattened lenticular form.